Hello, everybody. Thanks for coming to my talk. I'm going to talk about smart contracts, Solidity, and fixed point math. And my name is Paul Razvan Berg, and this is the Web3 track. We're going to talk about crypto and the development side of things, not the speculation side. Who am I? Well, I'm primarily known for being the co-founder of Sablia, an Ethereum-based payment protocol with currently more than $100 million in volume. I've been a smart contract developer since 2018, primarily focused on Solidity, and I'm an active open source developer and contributor. It just so happens that today is a very special day in Ethereum and in Web3, and I would even say more than just Ethereum, the entire internet. Today, I think it's 6:42 UTC, which is 8:42 Germany is our Ethereum. The Ethereum merge happened, which is this event that transitioned to a more sustainable, scalable consensus mechanism. All you need to know is that this has reduced the energy consumption of Ethereum by 99.95%. And that translates to a global reduction in energy consumption of like 0.2%. And that happened today. So, huge shout out to all the people who put in effort into making this happen. It's an amazing feat of engineering and human coordination and cooperation that spans 6 years of research, development, and so on. Which all concluded today. So big shout out to the Ethereum Foundation and everybody who was involved in this. It's sort of an honor to have a presentation today. So great stuff. Right. So let's start with the basics. What is Solidity? It is the most popular programming language for writing Ethereum smart contracts. And smart contracts are these immutable scripts that run on the Ethereum virtual machine. If you're familiar with the Java virtual machine, it's analogous to that. It's super different, but it's still a virtual machine that runs on the computers which sync the Ethereum blockchain. It's high level and object oriented, and it's been influenced by C++, Python, and JavaScript. So the learning curve is actually quite little if you have previous experience with this with these languages. Right. So what is the problem? Why is fixed point math such a hassle? Well, Solidity doesn't have fixed point types, and it neither has floating point types. If you think about JavaScript, you can literally write something like 0.5 multiplied by 1.2. Well, you simply cannot do that in Solidity, and the main rationale is in a blockchain context you want to have determinism and full predictability of what's going to happen with the set smart contracts because they're immutable, so you don't want funky things to happen after the contract was deployed. So that's why so far Solidity didn't add support for these kinds of variables, and to my knowledge they will probably never add support for floating points due to obvious reasons that will lead to non-deterministic behavior. Right. Solidity doesn't have built-in advanced math functions either, like logarithms, and this is sort of like a consequence of the first point. If you need to do anything complex, logarithms, exponentials, square roots, and all of that, you're pretty much on your own. If you just look at the Solidity docs, you'll not have any sort of guidance on that. And implementing advanced math functions from scratch is hard. Even if you have a computer science degree, you still have to go to Wikipedia and learn the specific algorithms and so on. Is just non-trivial. Right, and the last problem is that last year Solidity was upgraded to version 0.8, which was an overhaul of the previous versions. It's actually quite a big update. It made the language much safer, much easier to use, I would say, and it has all of those features which, while it takes some time to transition, it's totally worth it. But because many math libraries were written like 3 to 4 years ago, when protocols like MakerDAO, if you heard about it, were built the first time, people are still clinging to those previous like older libraries. So this is a problem. Like when you want to build a project in Web3 with Solidity, and it's anything more complicated than a simple dApp with a counter, you'll probably run into things like percentages and proportionalities. It's finance, right? So you have all of these interest rates and derivatives. And there is this thing called automated market makers, stands for like AMM. And AMM is a fancy way to refer to a money robot. It has some fixed rules. Again, smart contracts are immutable. So you just pass in some numbers, and it outputs. It gives you a fixed price for a trade. And of course, to calculate prices and take ratios and all of that, you need decimals, you need fixed point variables and so on. And finally, if you want to build any sort of custom trading algorithm, maybe you want to have like an arbitrage bot or something like that, again, you'll probably bump into the need of like having a fixed point math library. And I can testify to this. I'm an active contributor to the Ethereum Stack Exchange website. I'm pretty much logging in every day, and this question of like, how do you represent decimal values in Solidity? It's something that I see almost on a daily basis. Like somebody chimes in and asks, okay, how can I do this? I just can't define, again, 0.5 or pi or whatever. And as you can see, it's a known problem in the developer community of Ethereum. Right. So what I'm presenting to you is my solution. It's called PRBMath. You might notice that there is a connection between my name and the name of the library. I honestly didn't have a good idea for how to name it, so I said my name initials. In the context of Ethereum, that is a good thing because it means accountability, right? I can't change the code, so it means that I really have to make sure that the code works and there are no bugs, because if there are bugs, then because of immutability, the bug will be there forever. So that's it about the name. And the main advantage here is that you don't have to reinvent the wheel. As I said, if you want to build something like a log2 function, you need to go to Wikipedia and check out what scripts you have, like what algorithms you have available, and so on. You need to convert them into Solidity, which just takes time. I needed this myself for my own projects, and I saw no good offering on the table for the latest version of Solidity. So I set out and built it in 2021. And PRBMath is a modern fixed-point math library that operates with 18 decimals. That means that number 1 in normal mathematics is represented by 10 to the power of 18 in PRBMath. As I said, I leveraged the latest features added in Solidity version 0.8. The two main features here that are worth mentioning are user-defined value types and custom errors. I'll talk about them briefly in a future slide. All right, so the library is feature-rich. You have logarithms, exponentials, square roots, and more. It's still gas efficient, but user-friendly at the same time, and it's well documented and commented. A pet peeve of mine is when I see a function in a smart contract which is not documented. It's like you ship a hardware product with no user manual, again, because due to immutability, there's no way you can change the code once you ship it. So if you don't put in any comments or explanations, it's exactly like shipping a household appliance with no installation instructions. So PRBMath has all of that, and I think almost every single line is commented with like English comments, which go into how that specific bit of code works. Okay, so what are the basic features? You have average, division, inversion, that is 1 over x, geometric mean, multiplication, and raising to power, raising to a whole power. And the more advanced features, you have exponentials, which is raising the e number, Euler's number, to some value. Binary exponentiation, which is raising 2 to some value. Logarithms, the natural logarithm, binary logarithm, common logarithm. And the power function again, but now with like arbitrary exponents and the square root function. All right, so now let's take this for a spin. Let's see how it works in practice. Let's say you're a developer. You're seeing this on GitHub, right? How would you define your numbers with this? And let's see how we would define 0.09, 1.25, and pi, because pi is cool. And the PRBMath ships with this special variable type called UD60x18, which basically means that it's a number with 60 digits and 18 decimals. Why 60 digits? Because that's the largest you can fit in the UIint 256 that is the largest variable type in Solidity and in Ethereum. That is the standard size of an Ethereum word in the Ethereum virtual machine. So it looks like something like this. You just import the type, it looks like this, and then you use the wrap function. And you can actually type 0.009, but you have to add the E18 qualifier, which is the scientific number notation. And you have access to fixed point types. After you define these numbers, you can call and use them with all the functions that I mentioned before, the basic functions, the advanced math functions. So you can take logarithms and combine them in any way you want. In principle, you should be able to build any financial app just with this primitive here. And now let's go to another example. Let's calculate 3.14% of 1,729. The result should be 54 point something. This is a more complete code snippet. As you can see, again, we have the fixed point number definitions. And the trick is you assume that number 1 is 100%, and you can import what's called a scale. The scale is basically number 1, like 10 to the power of 18. And you multiply x by the scale, and you divided it by y, and you get the percentages. So pretty simple, but if you go under the hood, there's quite a bit of code that I wrote just to enable this, because there are some special edge cases. For example, when you multiply two numbers, if those two numbers are higher than the maximum value permitted by the UIint 256 type, then the intermediary result will overflow, but the end result wouldn't. And you don't want that. Like, you don't want an intermediary overflow, which will cause the transaction, your Ethereum transaction, to stop, to revert, because the result is still fits. And the solution for that is called Maldiv. It was authored by Remco Bloemen, an Ethereum researcher. And I re-implemented his Maldiv in PRBMath, so you don't have to think about it. Right. And now I'm going to show you the most complex example that I use the library for in my personal projects. It's called Yield Space AMM. I wasn't the one who created the AMM. It's a company called Yield who did it. I just implemented the formula. It's not worth it to go over what the formula means. I just put it here for basically showing off that you can implement stuff like this with PRBMath, where you have multiple variables, complex exponents, fractions, and time and subtraction. And that complexity is boiled down to what you see on the screen here. It's just 6 lines. You have the basic stuff like addition, subtraction, but you also have raising to power, and you have inversion there as well. And this is it. And you can do stuff like this. Oops. Right. So the cherries on top of PRBMath are the version 0.8 features. And there are custom errors, user-defined value types, and unchecked arithmetic. If you're going to build a Web3 app, do use these features. They are going to save you a lot of gas, will make your code more readable, more elegant, I would say, and it will just give you type safety, especially for user-defined value type. So what you've seen before with UD60X18, imagine that before user-defined value types, you had to remember which of your variables were fixed point types. So you had the same UIN 256, but for all the variables in your code base. So even if some number was an actual fixed point type that you needed for your Web3 logic, for your AMM logic, let's say, and other numbers were just simple human numbers, then you had to remember which one was fixed point and which one wasn't. User-defined value type solves that, and I presented you before how they look like. Custom errors are, again, a version 0.08 feature added very recently. And the biggest advantage with them is that they're super gas efficient. They're like 10x more gas efficient than the previous solution, which was to revert with a string. Like the actual, sentence, you emit that on the Ethereum blockchain, and your users would have paid for that. And it's non-negligible. It's like your user pays $1 just to see the error, whereas with custom errors, you get the same thing. You can still see the error, but it's just like 10x cheaper because they encode, they hash the error, and they just put in 4 bytes in the smart contract itself. And I argue this is the future of Solidity error reporting. And this is how the custom errors for PRBMath look under the hood. Again, to my knowledge, PRBMath is the only fixed point math library in Solidity which has custom errors, which should save you some gas. I didn't compare, I didn't check whether over the last few months they implemented this as well. But when I did check this, was like 6 months ago, PRBMath was the only game in town which enabled this new custom error feature. Right. So what about developer experience? As I said, I care a lot about explanations, about comments. And that's why I wrote NatSpec comments everywhere. If you don't know what NatSpec is, it's basically the similar to JSDoc, where you have the tags and specific tags which you add before a function. And that can be used to generate documentation automatically, which is super helpful for developers, but also for users of the library, because you can see very clear what it does. But I went the extra mile and added comments in the function bodies. And I would argue the installation guides are clear and it's simple to use. You can install the library both using the npm package way and also with Git submodules with Foundry. And you don't have to take my word for it. I put in a screenshot from Twitter from a PRBMath user saying how satisfied they are with just the documentation part, not the gas efficiency or anything like that. Just the fact that every line is explained and it's easy to pick up even if you're not an expert or like a mathematician, right? What about testing and security? I wrote 1,400 tests. I took into account domain boundaries, inflection points, in various other edge cases. Yes, this was rather boring, but I had to do it. Like if you have a bug in like a math library that can have a lot of consequences. And luckily today there wasn't any major problem found. There were a few minor rounding errors and so on. But after more than 1 year, the library has stood the test of time, and the library has around 96 test coverage. And soon I'm going to switch to Foundry. If you don't know what Foundry is, it's the first really well-built and scalable Solidity native framework for development, which means that you can write the tests in Solidity. When I wrote this 1.5 years ago, like Foundry didn't exist, and I had to use JavaScript and TypeScript to write the tests. But yeah, that's it on testing and security. And I guess that's it with the presentation itself. Thanks for coming. I put in a QR code in the last slide if you want to see the source code. And you can find me on Twitter and on GitHub at the same username, which is Paul R. Berg. If you have any questions, either here or in person, do please reach out. I'm very much looking forward to helping you and giving you support while you work with PRBMath to build your Web3 project. Thanks for having me.